So any of an electronic product which is having some sort of an intelligence, even a very small of an intelligence, like twinkling light has some sort of an intelligence of the timings, the patterns it can change based on the timings. That has a small intelligence is there, right? So even any of electronic product which requires power and which has even a very small amount of intelligence will have some sort of a microcontroller inside it, right? You told IC is, that is the integrated circuits. It is not necessary that every IC is a microcontroller. There is a certain of a differentiating lines are there. There are the there are the variety of the integrated circuits around you. Some will be only used for certain of a specific purposes, like you might have heard of 555 timer ICs. So that 555 timer IC is made only for generation of a particular of a frequencies which you set for it. That's it. This is an IC. This is a ASIC based ICs. Then there will be certain of a integrated circuits which is used only for the reading of a voltage, or maybe just for a frequency counting or a timer giving or anything. That is a made for a special purpose, and that is a hardware based. You can't change anything into it. If you have to use it, you need to implement into your circuit and make the proper schema, the electronic components around it, and it will start functioning. So that is IC it is called, and they may be ASIC in a nature, they may be particular function in a nature. Then it comes the processors. So laptops, computers, everything is having the processor, and the processor is there, which is having only the processing abilities, the ALU unit and the some registers are there for the processing of the activities only. And that is, and for execution of any of a thing, it requires a it requires a memory to be attached with it. It requires a RAM to be attached with it, and it requires the other of a peripherals also, which is a which may be like a timer, which may be like some kind of a battery devices just to arrange the frequencies. So external peripherals you will require in terms of the memory and all, if you are using a processor. And that's the same there with your computer and the laptop, because once you are going to assemble any of your computer, it requires the RAM, hard drive, everything needs to be attached with your microprocessor, and then it starts functioning. So it started with this, the earlier days, electronics started with this only. Maybe still in your lab, microprocessor lab, earlier it was in the syllabus. I don't remember that whether it is still there or not, but 8086, 8085 was there, where the microprocessor lab, the things that you have to attach separately the different peripherals along with your microprocessors, and then you can do the lab. But things have improved very high since then. Now, in a single of a chip, in that chip which I have shown you, or maybe Arduino you have used, in that Arduino also there is a microcontroller, that is a AVR microcontroller. So in a single of a device, you have the everything. You have the processor, you have the memory, you have the the storage capacity, you have the RAM capacity, you have the peripherals, everything it is there. And that's how a one single chip is able to perform multiple of the activities. But how it will perform, not based on the hardware only, you have to write some software for it. So that software we will be writing on our computers. That software will be getting fed into the memory of the microcontroller or of that device through some certain of a means. And then the device starts functioning for our purposes. So like there are the microcontrollers like Arduino device, maybe you have used. That Arduino, some of the times you can use it for maybe weather sensing. The same Arduino device, you can use it for some of the time for LED lighting patterns. The same Arduino device, maybe you can use for alarm generations. The same Arduino device you can use for cloud connectivity. So here is what the Arduino device is same, the microcontroller is same, but every time we are writing some new firmware and getting fed into the memory of the microcontroller, it starts functioning like that. So that's how the microcontrollers are the specialized categories of the chips or ICs, which you call, and which is having the memory, processing abilities, RAM, and everything on a single chip, and through which we can do the smart functions around us. Is it clear now what the microcontroller, microprocessor, and the normal ICs are? Anyone is still having doubt? Can raise his hand if any doubt, if anyone. Okay. Okay, so moving ahead. Thank you. So moving ahead, today we are starting with embedded systems and IoT. Here are the two words are there. And this for designing of any of an embedded system, the microcontrollers are there. And before we go ahead, embedded systems, I would like to hear from you. What is your idea about the embedded system? Can anyone just give me some definition or introduction about the embedded system?
Sir, it is a combination of hardware and software components to perform a
Okay.
specific task.
Great. So something here. Okay. And anyone else? Okay. Combination of hardware and software. Okay. Any other definition if one is having, which is different from this? Okay. Okay. So from where this word has came, it is a good answer. Combination of a hardware and software, but there is something more to this. So from where this word came actually, embedded means which is something inside. So today it is the introductions, thereafter the memory organizations, about the IoT, and then the microcontrollers we are specifically going to learn about. So embedded means which is something inside. So embedded system was conceptualized as a special purpose system in which the computer is completely encapsulated by the device it controls. Any of example you take, like a air conditioning device. So air conditioning device in itself is a system. So it has the multiple of components of it. It has the ducts, it has compressor, it has the pipes, everything is there, and it has the temperature sensor. Apart from this, along with all these items, there is a one specialized system, that is a one specialized electronic system working within it, whose purpose is to give the control of these devices. Like there is an electronic system which is going to control the compressor of the air conditioning device. There is a electronic system which is going to control the fan motor of the air conditioning device. So that specialized system, which is encapsulated within the complete of a larger system, is the embedded system for that. So like the system, this specialized system, which is going to control the activities of the air conditioning device, is the specialized system for that AC. Why I am saying it as specialized system? Because in your fridge also there is a compressor. In your fridge, again the same compressor, by changing the activities of the compressor, the temperature is maintained. And in AC also, we are managing the activity of the compressor to keep our room temperature in the control. But is it possible that the electronic device which is inside of a AC can be used for the fridge? Do you think, is it possible? Yes or no? At both of the places, whether it is an air conditioning device or it is the fridge, in both of the places, there is a same electronics. The purpose is the same. The purpose at both of the places is to use the compressor and control the compressor to keep the temperature under control. And for that, there is an electronic system. But for fridge, we have a separate electronic system. for air conditioning device, we have a separate electronic system. There the separate electronic cards are there. So I'm just asking, so mechanisms are different. Okay. So it means that we can't interchange, though functions are, it seems that the functions are the similar, but we can't interchange them because our user conditions, our capacity of the compressors, our temperature ranges are altogether different. Our capacity of the compressors are altogether different. So that's why the specialized system it has become for AC. There is the separate specialized system for the fridge. There is a separate specialized system maybe for the chillers. There may be a separate specialized system for a furnace, the cool furnaces. So that's why for separate systems, these all are the larger systems. The fridge in itself is a system. The AC in itself is a system. The chiller in itself is a system. But to control the activity of these systems, there is a small system working within it, which is going to control the activities of these larger systems. And these are specialized for that particular type of a system. We can't interchange it. It is same like the motherboard of maybe Intel processors can't be interchanged for a Celeron processor or maybe for AMD processors, because the systems have been designed like that only. So based on the capacities, based on the functions, based on the specifications, these systems are specialized for each of a larger system, and it is going to control that only. Also, it is like we have I have an LG air conditioning device. You have a Godrej air conditioning device. Person C has a maybe IFB air conditioning device. Even we can't interchange the electronic systems for all these air conditioning devices. The air conditioning, the electronic system for IFB AC will be particular for the IFB only. We can't use it for Godrej or maybe for LG. Because again, there are the specifications, there are the control codes, there are the control commands, which is specialized for that company only, and we can't interchange them. So that's how these specializations of the special purpose systems are developed based on the platforms of the hardware and software both. So that's why it is a combination of this specialization we are giving based on the combination of the hardware and software both. And here we don't term it as a software. Software we term whatever we are writing for work on any of a computing system, that is the software called. But once we are writing those softwares for any of a hardware device to operate, for the software, the program which we are writing to go into the memory of the microcontrollers, these are called the firmwares. So from now onwards, you will not use the term as a software for your microcontrollers. You will always be using the term as a firmware. Got my point? It is FIRMWARE. So this is our firmware. Whatever the program that we will be writing, it will be in terms of the firmware designing. So in embedded systems, IoT systems, whatever we are learning, we will be using the microelectronic hardwares, the microcontroller based hardwares, devices, and better word is the peripherals actually. And we will be writing the firmwares to use these peripherals with the microcontrollers. Once we will come in the IoT domain, and then we require the data to see whatever the data that those we are gathering from using the microcontrollers and sending to the cloud for the analysis purpose. And once we require that analysis needs to be done, that time we may need to design some software. So at that time, these are the platform independence will be there. So softwares has the platform independence, like your MS Word, MS Office, this Zoom, all these are the softwares because they can run on any of the computer. We don't require, like even if I am a Windows 7 or it is the Windows 10, only certain of the files will change maybe for the as per the version, but overall the software remains the same. But once we are designing any of a program for our microcontrollers, so maybe you have designed it for Arduino, that program won't work for microchip. And even the different versions of the Arduino, like if you have designed it for Arduino, the same of a firmware, the same of a hex file, you can't program it into the Arduino Mega, because the microcontrollers are different. So that's why you have to select this different board while doing the programming, and then you can feed the program into the different boards. So at the top level, it seems same, but at the lower of a level, hex file, the complete of a file changes. So firmwares are actually platform specific. Whatever we are writing, those are specific to the platform. So embedded system is, that's why, as a special purpose system where computer is, you're completely encapsulated by the device it controls. And that's what the differentiating figure from a general purpose computer is, because in your computer, you can do n number of things. The computer which we are using, it can, using this computer, we can play music, we can view videos. We are doing right now online call. Thereafter, using the same computer, I can write the documents, I can go to browser, I can browse any of a thing. So computer can do n number of a things, but the microcontroller based system which you are designing, it will be specific to a particular of a task. If you have designed it for the fridge application, it will be for the fridge only. If you have designed it for a maybe car automation, that will be there for the car automation only. It can't be used for the another purposes until and unless you have not changed your hardware, you have not changed your firmware. So changing of the hardware and the firmware, both are required to make it usable for the another purpose. And if we have changed both of the things, it means it become a new system. But the same thing is not true for our computing systems. Using the same computer, we can do n number of tasks. So that's what the differentiating factor between a computing system and an embedded system is. In computers, computing system is a generalized in a nature. You can do any of a thing, where the embedded systems are specialized in a nature. You can only do what the task that you have been designed for. You can't vary from it. Till now, hope, is it clear? Keep the system.
Yes, sir.
Yeah. Now there is a certain of a times, there is a confusion comes in the mind that what the PDAs or mobile phones, what are they? Are they embedded systems or are they computing systems? Because earlier generation, like the mobile phones, which were keypad based phones, Nokia phones maybe, they were specialized for a particular of a purposes, like your like it is the doing the calls only, doing the SMS only, certain of alarm features. So they were specialized and they were in the category of an embedded system only, because for what purposes it has been designed for, it was doing only those activities. You can't change operating system in them. You can't add any more function into them. So those were the embedded systems. Those were specialized. But nowadays, smartphones, which is there in your hand, you can do n number of things. The call and the SMS is the basic facility. On top of that, there are the n number of activities you can add into your phone, and it is almost acting like as your computer. So whatever the activities which you are doing in your computer is the same of activities that you can do in your mobile phone also, in a reduced of a screen size only. Even now the mobile phones are having the higher of a processors in many of a times compared to your computing systems. So as per the nature of this hardware design and as per the expandability of the software, because now the mobile phones have the software, they are not the firmwares only, because they are expandable in a nature. Their platform independence is coming in due to the various versions of the Android. So as per the expandability in the nature of the software, this line of definition between the embedded system and the computing system is continually blurring, because the embedded systems were specialized in a nature. So that's why the microcontrollers were also of a low capacities. The pins, the memory capabilities, the RAM size, the program memory size, everything was limited. I'm just telling you that when I started my career in the design of the embedded systems, I'm talking about in year 2006 or 7, that time, if we were designing a program size of a 2 KB, that was a talk of a town. Normally, the programs were designed in a range of only 700, 800 bytes or maximum of a 1 KB or 1.1 KB. Those were the program sizes. But nowadays, we are easily designing any of a program which is having a 30 KB, 32 KB size. And now the microcontrollers are also generally available in 32 KB size. That time the microcontrollers were like 8 KB microcontroller. The program memory of the 8 KB microcontroller was very costly, and those were rarely used in the applications. Generally, the microcontrollers were used of 1 KB or 2 KB in the program memory size. But nowadays, the common program memory size is 32 KB, which you are using in your Arduino devices also. And it is going 128 KB, 256 KB, such kind of a sizes. So there is this memory capability is increasing. So same way, the complexity of the programs are also increasing. Earlier, it is only the systems which were there for the taking certain kind of a data and doing the small activities, to now using a single system, we can do n number of tasks like your mobile phone. And that's how this line of definition is continually blurring, that embedded system is a part of a system. Now embedded systems are itself becoming a complete system in itself. Lots of example you can see around you, like weather systems. So that weather system in itself is now a complete system. It is having the sensors, it is having the microcontroller, it can gather the data, it can send the data to the cloud on itself. It does not require any computer to connect with it. And it can do all the activities. Even it can send the data on the display also on the LED boards. That is again a part of an embedded system. But earlier, if we have to do all these activities, so we were like that time when these high capability microcontrollers were not there. That time, what we need to do, that we used to have some sensors, and there is a small microcontroller. We gather the data from using the sensors into the microcontroller and send those data to the computers. And from computer, we used to send the data to the cloud level or to the web server level. Even cloud was not there. So at a personal web server level, we used to send that. So that time, the microcontroller were just a very small part of it. The larger systems were the computing systems. But nowadays, every of a thing that we used to do using the computers are possible to be done within the microcontroller itself. There is no requirement of a separate computing system. There is no requirement of anything. Directly from your device, we can connect to our cloud, and that every of analysis, every of a thing that can happen at the cloud level. So this definition is continually blurring. And as the softwares, as the processors will be keep evolving, the embedded system in itself in many of our times will become the complete system itself, right? So that's why there is a huge demand of the professionals are there now who can work on the bridging of these things, on the evolving of the processors, who can work on and can define new standards of the systems, which will be self-functional, self-motivated, and working on its own as a complete system. So there are certain examples around us of an embedded systems like the routers, the networking devices, ATMs, avionics. There are the lots of embedded systems are there at every of a place. Cellular telephones, earlier telephones, automotive electronics, thereafter your home automobile products, or home automation products, calculators, household appliances. So there are any of a domain, any of around you. If you will just move your head in your house, there will be hundreds of products. You will find that there is some kind of a smartness in them, and there is a microcontroller inside it. So if there is so many of a huge requirement is there, definitely there must be the design requirements also, and we should be on a path to learn that how to design these systems so that we can progress our professional life. So just an example of a domestic fridge I was talking about. So how the domestic fridge has an embedded system. So the fridge is your complete system. Now in this fridge, there is a small microcontroller is there, which is taking care of your control, the alarms, displays displays, thereafter your temperature recording, that there is a required temperature it is, and then there are the uh, actual temperatures. So based on the reading of the actual temperature and the compensation with the required temperature, the compressors are controlled, and that's how the temperature within the fridge is maintained. Then we have the human interaction. So if we open the gate and we keep it open for a longer time, the alarm rings in the fridge so that the gas should not leak. And then there are the fridges which can be controlled using your Google Assistant, or maybe the fridge can be connected over internet, and you can know the status of your fridge in a real time. So just fridge is a larger, there is the mechanical housing and electrical parts into it. But to control all of these things, these functions are required. And to provide these functions, there is a specialized system into this, that is the embedded computer is there. So what are the, for reading of the temperature, we need the thermistors or the sensors. For compressor control, we need the drives to control the things. To display, we need the display devices. To raise the alarm, we need the buzzers. To know the human interaction, we need again some sensor which can sense that whether the gate is open for a longer duration of a time. And once we are going to connect it over a network, so that will be the IoT part. We can connect it through Wi-Fi, we can connect it through GSM, or if it is a local connection we are doing, so we can connect it through Bluetooth. So all these things are there, and all these are the components of your embedded system part. So whatever the learning that we do inside of the embedded system, all these are required to develop the systems which will have all these components. Again, one more example of a car door. Every one of us has are using the cars. So in window, like just in the window only, what are the things are there? Window motor is there. So through that, the window, using the window motor, the glass rolls up or down. And then if we put our hand between the window and its lock position, the window stalls. So it means there is a sensor which takes care of the window stalling, so that if the hand is sensed, so window rolling will stall, so that the sensor is there. Then there is a lock control and lock actuators are there. So remotely you can lock also your car, or maybe once you lock it gets completely locked. And if it is not locked, so there is the open door sensor, and if the door remains open, you will get alarm on your dashboard. Then there are the window control buttons. So you just switch on the window control button and the window glass starts rolling up or down. So in a one car door, there are so many functions, and for all of them, there are the specialized systems are there. If a complete car, if I'm talking about, so it is the dashboard control systems are there, steering positioning systems, airbag control systems. So if airbag opens up, if any of an accident is sensed, so airbag opens. So that is a separate system for it. Then the climate control system, driver seat positioning system, infotainment system. So all these are the separate systems working in the car. And then there is a ECU, the electronic control unit is there, which is communicating, which is taking care of the communication between all of the systems, and then the complete of the activity of the car is managed, and all of them are communicated through a certain protocol. So in automotive world, there is a protocol called CAN protocol, the controller area network protocol. Now it is common in other of the domains also. So all the places now where there is a requirement of a multiple embedded systems to be connected and communicating with each other, there is a requirement of some protocol, and that CAN protocol is now used widely in all of these domains. So that's how the embedded systems can work as a alone. Embedded systems can communicate with other embedded systems also based on a certain of a protocol, based on certain of a communication protocol, and a central control can take care of the communication of all. And also, once we require this communication to happen across the borders, across the borders of your home, across the borders of your city or your country, then we require some wireless protocols to operate into it. And that's where the internet connectivity is required. And that's how the IoT term comes into picture. So this is another example. So this thing is important. I think if the pen is around, you can note it. So embedded system block diagram, in an embedded system, the central is the embedded computer. That is the microcontroller. Physically, it is the microcontroller. That microcontroller is having the hardware. There are the transistors within the microcontroller. And then there is a software in the microcontroller. So that is the firmware term is. And the firmware is the heart of your microcontroller. And whatever the logic, whatever the program that you feed in, that goes into this embedded computer. Now, this embedded computer has the logic and everything, but to work on it requires a certain inputs. So those inputs are in terms of the signals. So signals, so whenever any of a signal comes, there is a signal conditioning is required. So maybe your signal is of 100 volt, 200 volt, 220 volt, or maybe a negative voltage. So there may be might be a AC pulse. So the signal can be anything. Might be by temperature. You want to record the temperature. So there will be the temperature. The physical quantity is the temperature. But your microcontroller understands only certain of a specific signal levels. Normally, it is the 0 volt to 5 volt is the signal levels that microcontroller understand. Nowadays, the microcontrollers are also working at a 3 volt level. So at that time, we can maximum the signal level we can give is 3 volt or 3.3 volts. So depending on the voltage signal levels of the microcontroller, we have to condition the signal. We have to either step down or step up the signal, and then we can feed them to the microcontroller. Directly, we can't feed any of a signal to the microcontroller, and that's why the sensors and transducers are required. So once we feed them, and then there is a requirement. So there is a signal conditioning is required. And then at some of the times we require the data conversion, because microcontroller is a digital device. So it only will understand the digital data. If it is an analog data, it won't understand. So that's why we need a conversion, the analog to digital conversion, or maybe a discrete to digital conversion. So that's what we require. And once we convert the data in the form of the understanding of the microcontroller, then the logic is applied. And based on your logic, the output gets controlled. Like, for an example, I'm sensing the temperature of this room. And once the temperature is maybe below 20 degrees centigrade, I want to switch off the air conditioning device. So signals are coming here, and signal is conditioned. That temperature data is conditioned in terms of the voltage. That voltage is brought in the range of a 0 to 5 volt level. That is being fed to the embedded computer. And this logic is here that if the temperature goes below 20 degrees centigrade, so if this comes in the memory of in the processing capability of the computer, there will be output drive. There will be some relay or kind of control devices, the output control devices, which will turn off the mains control of air condition. So that's how the complete logic will work. Now, to work this system, there will be certain of user inputs may also be required for that purpose, or you want to display something to the user. So for that purpose, the displays and keypads are there. And if we want to connect this system with other system, so there will be the network interface, and that's why the link to other system. So like if it is a part of another system, so that's why the link is there. Or if it is a part of a networked system, so that's how also the link is there. The block diagram is clear?
Clear.
Okay, one more important part. So principal function of an embedded system is not computational, but to control. So yeah, that is also one more thing that I forgot to talk about. So computing systems are general purpose systems, and it's the purpose of the computing system is just compute, like the computer that is in front of us. Its purpose is just to make the communication between me and you, or maybe doing some certain calculations, doing some word processing. If you want to control the air conditioning device through your computer directly, it is not possible. You have to attach certain of a peripherals, then you have to write some software for that, and then it may work. But so the purpose of the computing system is to compute, to do the calculations. But when we design any embedded system, the purpose of the embedded system remains to do the control. So whatever the electronic system we are designing, the purpose of those electronic smart systems remain to control the system, like to control the air condition, to control the fan, to control the fridge, to control the car. In the embedded system, we don't expect them to do the any kind of a computing, just to do the calculations. For the calculation purpose, we don't want any of an embedded system. So always embedded systems are for control purposes, and computing systems are only for the computing purposes, for the calculations purposes. And that's why the design nature is also different. In your computing system, here we have a CPU, we have only a CPU, and the memory, the data memory, that is RAM, the program memory is separate, IO unit is separate, and then it is connected with the outside world. There is a no peripheral, there is a no special software that is required with the CPU, and it is just only going to compute the things. Whereas in the embedded computer, with the processor itself, there is some firmware is been given, and its purpose is to do the control of the things. And that's why the nature of the work, the nature of the design, everything is different of embedded system from a computing system. So just keep it remembered that embedded systems are there for the control purposes, and this control is possible through the embedded computer along with the peripherals available within the microcontroller. So we will be discussing what are those peripherals are in later of the sessions, but the peripherals are actually for the control purposes. Now, these two are the architectures. Have you read it before? This architecture of the processors?
No, sir.
No.
Yes, sir.
Yes, you have read. Can you just explain a little bit, if you remember? Any explanation? There is another name for this also. Give me the name. Remembering? No. Okay. So von Neumann architecture is also called CISC architecture. And Harvard architecture is called RISC architecture. CISC means complex instruction set architecture, and RISC means reduced instruction sets architecture. So what is the meaning of this is? So whenever any of a computing, any of a system is designed, whether it is your embedded system or it is your computing system, these four are the important part: the CPU, the data memory, that is RAM, the program memory, and the IO unit. These four are the important part. In your computing system, physically, the CPU, the data memory, program memory, IO unit are separate. Whereas in your embedded system, the CPU, program memory, data memory is within a single chip, as I have shown you. There is a no separate physical existence. But internally, all the four things are present, and there is a communication that is required between all these four elements so that any of a program should process. So in von Neumann, this is the earliest architecture. The von Neumann is the earliest architecture, and based on which your all the Intel processors, your 8051 processor, everything is designed. Even the earlier generation ARM was also based on the von Neumann architecture, CISC architecture. So what it has, whenever any of a program processes, there are the two things are required. One is the data, another is the program part of it, like instruction part of it. Like I have to add two numbers. So there is an instruction, add 2, 3. So here 2 and 3 are the data part and add is an instruction part. Now, when it goes for the processing, the instruction part is separate and data part is separate. And once both of them reaches to the processor, only then the processing of the activity that the any of a result we can expect. And once this result gets calculated, then it will come out on the IO lines. So if we have the separate lines for transportation of the instruction and the data from the memory to the CPU is there, if we have the separate lines, in that case, what will happen? That the faster execution of the program will be there. Do you agree? If you and me both has to go at a certain of a location, and only then some task would be achieved, and there is a single, there are the two separate lanes through which we are going, and we are reaching at a certain of a place. So we reach faster compared to that there is a single lane through which I will go first and then you will come, and thereafter we can reach at a certain of a location and the task will be achieved. So what is faster? If we both are going separately through two different lanes at a certain of a location, is it faster? Common question. So that's the same thing is there in these two architectures. The instruction and the data both has to reach to CPU, and only then this program can process the instructions, the program can process, your complete of a execution can happen. So in von Neumann architecture, what it was that we had a single bus through which the program, the instructions and data both will travel. So one can travel at a time, and that's why the instructions take time for the execution. But in a real-time system design, it is not feasible, because in a computing system, if we are using, so right, we are adding some numbers. Now addition of those numbers, if some of the times it is taking 1 microsecond, and some of the times if it is taking 10 microseconds due to certain of issues, there is a no issue into this. Even we can wait for 10 microseconds, even we can wait for 10 milliseconds, 100 milliseconds also we can wait. There is a no harm into this. And so even the in a computing system, if there is a no exact accuracy of the timing of the execution of the instruction, is the process will get delayed, but it is not harmful for our life. But if we are using any microcontroller based system, and microcontroller based systems are real time in a nature, and at that time, if like for an example, we are dealing with an airbag system, and the airbag is installed in a car, and the accident is sensed or a bump is sensed, then there is a fixed time for, like, once the accident is sensed, within 100 milliseconds of a time period, the airbag should open. Now, if the instructions are taking time to reach to the CPU, and maybe at some of the times it is taking 100 milliseconds the airbag to open, and at the some of the times it takes 500 milliseconds to open the airbag, will it be any use of that airbag in that case?
No.
No. So once we are designing any real-time system, always there is an accuracy of the time is required, the correctness of the time, and the assurance of the execution of the task at a particular time is required. And that's how the real-time systems are. Any of electronic systems which has to respond in a real time has to give the correctness and the accuracy of the execution of it at a particular fixed time. Whereas in the computing system, maybe right now we are opening a Word file, and if the no other process is running, the Word file can open within a second. And if there are lots of processes are open, the Word file can take 10 seconds, 20 seconds, or even a minute to open. But it is not harmful. It is not going to harm in my life. I'm not going to die due to this. But if the airbag does not open within that 100 milliseconds of a time period, the life of the passenger is at a risk. The life of the driver is at a risk. So that's why whenever the microcontroller based systems are designed in and whenever the microcontroller based systems are taken into consideration, they need to perform in a real time in a proper exact correctness of a time. So that's why this von Neumann architecture was not suitable for the microcontrollers, because there is a no accuracy and there is a no correctness of the time, or there is a no kind of assurance of the execution of the time is there, because there is a single lane. Once the instruction will process, only then the data can travel. So there is a no correctness and there is a no assurance. So that's how this architecture was designed, which is having the separate lines for the data memory, program memory, and IO unit to communicate with the CPU. And once they are communicating separately, then this the correctness of the time and the execution of the things are possible. So that's how the microcontrollers, the newer generation microcontrollers, are working on the Howard architecture, that is called the RISC architecture. And the older generation microprocessors, even your 8051 microcontrollers, are working on CISC architecture, that is complex instruction set architectures. So that's the difference in the memory organization is. So our microcontrollers which we are using are based on the RISC architecture, whereas the processors, the Intel processors, 8051 controllers, all these are based on the what? CISC architecture, that is von Neumann architecture. So that's why this CISC and RISC is there. Now it comes to the cyber physical systems. So embedded systems are designed for the special purposes. Now this embedded systems has other things also, the control, communication, and computation. So all these things make these systems as a cyber physical system, that is the sensors, networks are there for plug and play. The intelligent mechanisms are there as a part of a system. And once the embedded devices are connected to each other, that is the cyber world, cyber term called. And all of them are for the purposes of extracting of certain of an information. So transforming the interaction and control of the physical world around us through information is called the concept of a cyber physical system. And for that, we require the embedded system, we require the sensors, we require the connectivity. So all of them together are making a cyber physical system. And in the cyber physical systems, we require the concept of plug and play. So once we are doing the plug and play, it means what? Like pen drive that you have, that pen drive you takes and connect it into any of a computer, it starts functioning. Similar of a way, the cyber physical systems should be designed in a way that it can connect with any of a network at any of a time. It does not require any installation or any of a things. So that's how the concept of a plug and play is required in the cyber physical systems. The IoT systems, once we will be learning, so we will have the detailed discussion on the cyber physical systems. This cyber physical systems are more software configurable systems, and there is a connectivity between from edge to cloud is required. There is a machine health monitoring is required in this. That's through using this, we do the machine health monitoring. We need the security in these cyber physical systems, and more robotic integrations are getting adapted into this cyber physical system. So all the new generation systems, connected systems, where the smartness, the connectivity, everything is required. Those are the cyber physical systems called. Now, for working on all these systems, there is a microcontroller is required. So that's what we had discussed in the very beginning. So microcontroller or MCU is a computer on a chip, which is a type of a microprocessor emphasizing on self-sufficiency and cost effectiveness. These are the two things that is required. Self-sufficient because it has the memory, processor, everything. And then it is a cost effective because if your microprocessor you are going to purchase, it will take you thousands, 4,000, 5,000. But a microcontroller can start from 25 rupees, 30 rupees. So because microprocessors are versatile in a nature, you can do n number of tasks with a microprocessor, but microcontrollers are designed for a specific purposes. That's why they are self-sufficient and cost effective. This is in contrast to any of a general purpose microprocessor. Microcontrollers are to control with the help of a peripherals available within it, whereas the microcontrollers are good at doing one task at a time. So microcontrollers will do one task at a time. Like if it has to sense, so first it will sense, then you can do other activities. But in a microprocessors, there are the multi-core features, and in the multiple threads, the multiple tasks can be possible at the same time. But it does not mean that multiple tasks we cannot do using the microcontrollers. We can do multiple tasks also using the microcontrollers, but for that we have to give the feature in our firmware design. So there will be the schedulings we will be doing in the firmware design during your sessions, and using the schedulers, we can do n number of tasks using the microcontroller also. But at 1 t is equal to 0th millisecond, or maybe t is equal to 1st millisecond, it can do only one task because it is a single core processor. It is there. So microcontroller is basically a microprocessor which is designed primarily to perform simple control functions. It is a low cost, it is physically small, it is IO intensive, it is capable of EG interfacing. The limited memory capability is there for the program and data. That's because it has to do particular number of tasks only. And it should be able to operate in real-time environment. And in certain of our microcontrollers, we require the microcontroller to operate in hostile environment, that is high or low temperature, tolerant to electromagnetic interferences, all these things, like in a security device you are using. And that security device can be hidden at any of our places. There might be the microcontroller you are using for your grids. There the EMI interfaces will be there. So that's why microcontrollers should be able to operate in the worst weather conditions and the worst operational conditions also. And for that, we need to design the system. Also, it need to be designed that it should be able to operate on a battery, like a camera device, maybe an audio device, your Bluetooth audio, Bluetooth hands-free device. All these are working on the batteries. So that's why the low power it should be working on, whereas the microprocessors does not have such kind of features. So a general purpose microcontroller will have a core, microprocessor core, the internal data and address bus through which the program and data memory is connected. It is having the IO pins through which it is connected with the outside world. It is having the analog IO pins through which it can sense the voltages and anything. It has the counters and timers. Thereafter, there are the other peripherals for interfacing with the real world, other things like to do the communication, to do the pulse control, to do the CAN communication control. There are the peripherals, there are the internal devices are there, which is within the microcontroller itself. And by using the firmware, by writing the different firmwares, we can use these devices and we can do our tasks. There is a clock is required to work on this microcontroller. the power is required. The power is range from 0 volt to 5 volt. So on 5 volt, it starts operating. On 0 volt, it will be non-functional. Nowadays, they are 0 to 3 volt also. And then there are the certain reset interrupts. So if the microcontroller hangs because of your maybe lack in the bug in the software or due to certain of the regions, if the microcontroller stops functioning, the firmware stops functioning, that time we should be able to reset the microprocessor also. And once it gets reset, the microprocessor starts functioning normally. So these are the features are there in a general purpose controller. So microcontroller is microprocessor core plus memory plus peripheral. So these were the general introduction. Now in our lab, once the lab is starting, that time we will be using a particular microcontroller that is from the industry leading microchip PIC microcontroller. So PIC stands for peripheral interface controller. So these are the internal peripherals are. And in earlier microcontrollers, like even your 8051 also, if we have to do the functions, so we need to attach separate peripherals. Like if we have to do ADC, the analog voltages we have to read. For that, we have to attach a separate IC. If there is a computer communication we have to do, so for that, we need to attach a separate IC for that. So the peripherals used to be attached separately in an earlier generation microcontrollers. But to save the space and to keep the hardware simple, there is always a concept in the electronics to keep the component count minimum. If your component count is a minimum in the electronics, it means the chance of a failure is very less. So company Microchip started a project, and Microchip has developed the first controller which is having the peripherals inside the microcontroller itself. All these devices for the ADC, for PWM, for computer communication, all these things were put inside the microcontroller itself, along with the program and data memory and the microprocessor core. And since then, this journey of a PIC has started. And they are the leaders, that's why, since 2002, continually in the 8-bit domain, because of putting all the features, and now they are putting the resistors and capacitors also in the microcontroller. So you don't require even the passive components also on your circuitry. You will attach just a microcontroller and write the firmware for it, and your system is complete. So that's how the smartness, the portability, and the compactness in the size of the electronic products we are providing using these microcontrollers, the latest generation microcontrollers. So we will be learning how to use these microcontrollers in our lab sessions. But before of that, today we have a small introduction about the PIC 16F887, which we are going to use in our sessions, and something about the PIC 18F also later on. So I will be giving a detailed introduction on this PIC 16F887 in this session itself. But before of that, I'll give you a 5-minute break, and you go on a 5-minute break. It is after 5 minutes, we are connecting again, and then I will take you to this. If any question before leaving, if you have any of a question, you can write here. I'll answer that, and then you can leave. Okay, there is a question: if microcontroller has limited memory, how can we load C compiler into this? So we don't require to load the C compiler in the microcontroller. The C compiler is in our laptop or a desktop. We write the program on our desktop, and thereafter we compile it, and whatever the output file is generated, that output file goes into the memory of the microcontroller, and there the assembler is there. So assembler takes care of the instruction execution. We don't require any compiler in the microcontroller. Is it clear? Okay, so we are connecting again in 5 minutes. In the meantime, if anyone has any question, he can write it down. After 5 minutes, once we connect, I'll answer him. Okay, shall we continue? I think. Okay, so I'm continuing again. Many has left. Okay, so there is a question again that if user compiles a program in Intel computer, then bytecode generated may also be in Intel X assembly, then how can, yeah, very right question. So the compilers which we are using for the compilation of for the firmwares are actually called the cross compilers. So the nature of the cross compiler is that they will run on one platform, and the opcodes that they generate are targeted to the systems on which the file has to run. So that's why here the compilers, the specialized compilers for the embedded system, for the microcontrollers we are using, are the cross compilers we will be using. They will be running on the Intel systems, or maybe your Unix OS or Windows OS, anywhere they can run, for which they have been designed for. And and working on all of these platforms, they will generate the hex files. Those are called the hex files. They will generate the hex files targeted to the microcontroller for that specific microcontroller. So once we will be designing the software, you will see that I will select the microcontroller first, and then we will write any of a program so that the compiler can understand that for which set of a microcontroller, for which set of the microcontroller we have to write the we have to generate the hex file, and that's how it gets executed on the microcontroller platform. So this is the cross compilation part. This okay, Manish? This is a good interview question also. Many of the times the interviewer will ask you this, what is a cross compilation? So it is not a platform independence, but it is actually working on one platform and generating the opcodes for a different target machine. Okay, so any more questions? Anyone else have? Till now, session is understandable. Any problem if anyone is facing, you can also write. Or maybe just open your mic and you can ask me. Okay, till now clear to everyone, right? I'm taking this forward. Okay, so microcontroller is this PIC 16F887 we will be using in the lab first. So PIC is the peripheral interface controller. That is the brand name for microchip. 16 is the manufacturer series number. So microchip makes lots of microcontrollers, and that's how there are the different series numbers. So 16 is a one series number. F stands for flash. So this is a type of a memory. So we can program the microcontroller. Thereafter, we can use it. And again, if we have to feed a new program, we can flash the memory. So that's why this flash type memory is. Otherwise, there is another one is a CMOS type of a memory, where whatever you have fed into the memory, it will remain permanent. That is a one-time programmable. So nowadays, all the microcontrollers are flash in a nature. So that's why 16F, and 887 is the particular number of the microcontroller which we are going to use. Same of a way, PIC 18F, PIC is again the brand name. 18 is the manufacturer series number. So based on the certain of a differences, the manufacturer series number is there. F again stands for flash, and it is a 4550 is the number for the particular microcontroller. Both of these microcontrollers are 40 pin in a nature, which we will be using. And this is a 8-bit microcontroller. What is the meaning of a 8-bit, 16-bit, 32-bit is the RAM size and the data memory size of the microcontrollers are of a 8-bit or 16-bit or a 32-bit. Based on that, actually, they are categorized. Same way, if it is the computing world also, if your computer is 64-bit processor, it means the RAM size and the register size of the processors will be 64-bit in a nature. If it is a 128-bit, it means the RAM and the register sizes are 128-bit. Similar here also, the microcontrollers we are going to first use will be 8-bit. And once we are doing the IoT, at that time, we will be using the 32-bit microcontrollers. So it is a 8-bit microcontroller, which is there used for the design of any smart systems, the control systems. It means their register sizes are 8-bit. Whereas once we will be working with the 32-bit microcontroller, that time their register sizes will vary and it will go up to 32-bit in a nature. So within a microcontroller, what all things are there? There is a processing unit. So that processing unit has the status register, FSR register, mux, ALUs, everything is there. That is the processing unit. And then there is a RAM locations. So for the temporary or interdependent data storage, the RAM locations are there, which is called which is connected through a data bus. And then we have the flash program memory locations. So here the flash memory is 14-bit wide. Just keep it remembered. This program bus and the data bus are separate. The program memory size is 14-bit wide. This is the width. And the RAM memory size is 8-bit width. So our register sizes are this. Then there is a program counter. So bit by bit, the location by location, the program gets executed, and that is by taken care by the program counter. Then we have certain of a special features, that is the oscillators, thereafter the power up timers, watchdog timers. These are the certain of a special features of the microcontroller, which we are using for the functioning of it to give there are the hardwares, and to activate those hardwares, we have to use these certain of a features. We will be discussing them. So that is there with the processor. Then to give the timing, there is a clock signal is required. So either it can be an internal clock or it might be an external clock in 887. And for that, the timing generation system is there. The ports, these ports are the interfaces for the real world. So in the microcontrollers, you see the pins. The pins are, so any of a microcontroller, if you will see here it is. So there are the pins are there. In your Arduino, there is also a microcontroller, and through the pins, everything gets connected. So pins are the real world peripherals. The pins are having the numbers. But once we have to attach, we have to work anything with the pin, like you have connected any LED with a pin, like pin number 40. But how to tell in the firmware design, how to tell while designing the software for it, that I have to turn on an LED connected on the pin number 40. So for that purpose, the ports are here. So in the microcontroller, these are the ports, these are the registers actually, these are the memory locations. And from these memory locations, those external world pins are connected. Whatever we write on these pins actually gets reflected in terms of the voltage on those pins. So we write like a 0 on maybe if RA5. So here RA5, if you can see, it is here. It is on pin number 7. So if I write, for an example, RA5 is equal to 1, it means what? 1 is plus 5 volt. If our microcontroller is powered through a 5 volt, so 1 will be plus 5 volt. So plus 5 volt will be reflected on pin number 7. And if any device which is connected with the pin number 7, if it is an output device, that may get activated. So that's how the ports are the register locations which is connected with the microcontroller pins, and by writing the value on the ports, we can reflect those values as a voltage on the pins. So it is for the output. Same way, whatever the voltage that is there on the pin, if we want to read them, so we need to read them in the ports again. So for input and output, we have to use the ports. Those are the registers, and these ports are really connected with the pins on the hardware of the microcontroller. So that's how the ports are. In PIC16F887, we have 5 ports. It is port A. Here you can see it is the groups. So it is a port B. Here it is 4 pins of port D and 4 pins of port D. So total 8 pins of port D, 4 pins of C, and 4 pins of C. So total 8 for the 8 pins for C, 8 pins for D, 8 pins for B, and 1 plus 3. So total 4 pins for E, and 6, 1, 2, 3, 4, 5, 6 plus 2. Total 8 pins for A. So total how much we are having? 8 plus 8 plus 8 plus 8. That is 32 plus 4. That is 36. So this PIC16F887 is a 40 pin microcontroller, 1 to 40 you can see here from left top side 1, right side top is 40. Number, this is the way of counting the numbers. So from up to down, and then from down to up, the number counting happens. So total 40 pin we are having. Out of those 40 pins, 36 pins are there for the input output purposes. Here you can see the double side arrow is there. Double side arrow means the pin can be used for the input and output both. Whereas if it is only a single side arrow, it means the pin is either for only for input or only for output. So if it is like this, here on pin number 1, you can see only the inside direction is there. So that's why the pin is for the input purpose only. If it is like this, it means the pin is only for the output purpose. So here we have total 35 pins which can serve as an input output both, whereas 1 pin is there which is there for the input purpose only. So that's how the PIC pins are divided, and individually they have the names. Every pin has a name, and like RB0, RB1, RB2, these all are the port pins called, whereas collectively they are called as a port. So port A, port B, port C, something like this. So that's how total of 5 ports we are having: B, D, C, A, and E. So 5 ports we are having, and that's how the functions are there. So ports are there. Then we have the peripherals. So like timer peripheral, ADC peripherals, EEPROM for the memory storage, capture compare registers for comparing of the data, SSP for the serial communication, USART for the PC communication, comparator and voltage reference, lot more. So these are called the peripherals, and these peripherals are also within the microcontroller. And these peripherals are actually used for the purpose of doing any kind of a control of the external world devices. Apart from that, we require the power. So VDD and VSS. VDD is your supply voltage level. VSS is your ground voltage level. And MCLR is called the master clear reset. So there is a pin, particular pin. And by changing the voltage on that particular pin, we can reset the microcontroller. So all these are the part of this microcontroller which we have to use. In terms of the memory, we have the memories as the program memory first. So program memory is the location where your program, whatever the codes that you are generating after the cross compilation, and program them in the microcontroller, and that gets stored in the program memory. And here This program memory is 14-bit wide. It is a non-volatile in a nature. Whatever we have kept into it, it will remain stored even the power supply goes off. And total of 8 KB locations. This is having 8192 bytes of a program memory. Once we have to erase the program memory, or if we have to feed the program memory, there is a special circuitry is required, and there is a proper voltage level of a 5 volt is required to erase or to program the program memory. Then it comes the RAM. RAM is a location which is used by the program during the execution for storage of the runtime data. And here the RAM is available only 368 bytes. So just compare it with your system, which is having maybe 8 GB, 16 GB of a RAM. Whereas here on the microcontroller, we are only having 368 bytes of a RAM. So whatever the program we design, it has to be very concise in a nature and very specific. That's why a specialized programming skill is required for writing, and that's why we write the program in the embedded C language, not in a normal C. There is a certain of a differences we need to create so that the program size, the data size, everything should remain compressed, and that's how the programs can function, and it will not take much space in the memory. Then there are the SFRs, the special function registers. So as I told you that like here the pin, or there are the peripherals like timer, these all are the peripherals, external world peripherals, sorry, internal peripherals. Now to work with these peripherals, or like if we have to give the values on the pins, the voltages on the pins, we have to write some value in the some registers, and these registers are specialized, like with each of the pin number there is a particular register is attached with. So those are for the special functions. So that's why the SFRs are here, which is used to handle the internal and external peripherals of the microcontroller. Whatever the value during the program, whatever the value that we write on these SFRs, that is used to reflect in terms of the voltages on the pins and on the other peripherals. So that's why whatever every day a new lab, once we will be doing the lab, so every day some new SFR we will be learning. So actually, if you have to learn the embedded system, it is the microcontroller that you need to learn. And in the microcontroller, actually, we learn about the SFRs. So every day some new SFR comes, we need to learn what the function of those SFRs are, how to use those SFRs for interfacing with the real world peripherals. We write the program for the SFR based on the SFRs, and that's how our function happens. So those are the SFRs. And again, this is a part of a memory, part of a data memory. EEPROM is also one more thing, which is a part of a data memory. And this EEPROM is 256 bytes. So there are the certain of a times you require the data which needs to be stored permanently. Like we are using remote control devices, and like we are setting temperature of our air conditioning device. Now, if the power supply goes off, and once again the power supply comes back, we need the AC to start at the same temperature level, or maybe the TV device. So whatever the channel number you were viewing last time, when the TV opens up again, normally it starts with the same channel number. Our computer which we are using, whatever the brightness level, sound level we have set, the next time we will open the computer, it will start at the same brightness or sound levels. So it means what? These all are the data, but it gets stored at a particular of a location in the memory, that even the power supply goes off, it does not, the power supply does not, even if the power supply goes off, the memory does not get erased. So that's where this is the EEPROM location, where we need to write all these data, that even the power supply goes off, this will not be erased. And that is the location. This is our data. And for that purpose, there is a separate location, which is called as the EEPROM location, electrically erasable programmable ROM. And to connect and coordinate between all these, we have a CPU element, which is taking care of the coordinations. Apart from this, we have the IO pins, counters, timers, ADC converters, and all. In case of a 887, we have 35 IO pins of a multiplexed nature. One can be used as a timer, counter, serial interface, PWM, etc. PIC ports I had discussed with. So this SFRs are five for specifically with the SFRs. So our work with the PIC gets accomplished in a few special purpose registers. These instructions use these registers specifically, and instructions which affect the file registers memory can also be used on the special function registers by referencing the address of the SFR. So each of the SFR is having the certain of an address, and based on which they can. I just show you something. What are the SFRs are? Okay, so this is the data sheet of your microcontroller. I will share it with you, and the pins and everything. Now I was talking about the SFR. So yeah, here you can see. So to work with, like this is for PIC 16 of 882, then it will be there for the 87. Yeah. Here it is for 887. So you can see here, these are the SFRs actually. For each of the functions, like for timer, there is SFR, for status, for ports, for interrupt, for interrupt, for comparator, for port B, for ANSEL, analog selection, for these all are the separate SFRs which we will be learning, and each of the SFR is having certain of an address, like timer not is at an address 01, PCR is at an address 02, H means hexa. So hexa 01 location, hexa 02 location, hexa 03 location. So they are been addressed. Now, once we are writing the program, either we can pass the reference of these addresses or we can pass the name of this SFR. So what is convenient for us? Every one of you is having certain enrollment number. Every one of you is having some names. So is it easy for me to call you by name if it is a unique, or is it easy for me to call you by the roll number? Definitely by name. So if it is unique, and it's the same way in the SFRs also, every SFR name is unique. And that's why while writing the program, we address the SFRs by their name, not by their addresses. Also, these SFRs are in the different banks. These are all called the memory banks, bank 0, bank 1, bank 2, and bank 3. So it means the SFRs are grouped in a memory in such a way. This is a virtual grouping. This is not physical. Grouped in such a way so that the minimum in a minimum program execution time, the maximum of SFRs can be handled. Also, if you see here in the memory bank, these are the general purpose registers. So in each of the bank, there are the general purpose registers are there, which is called the RAM locations. And whatever the temporary data, the SFRs have the fixed values, and they have the certain initial values, whereas the RAM locations, it can be random. So whenever we write the program, any of a variable we declare, that goes in these RAM locations only, but their initial values are random. That's why we need to initialize each of the variable whenever we are writing the program. Without of an initialization of the variable, the program will not be successful. You may get the erroneous results. So RAM location is also in the memory bank along with the SFR, and whatever the variables we write in the program, they will get stored in these RAM locations only. So for the ports specifically, there are the 5 locations where these are the ports, and they are connected to the output word. Each bit in the port is connected to a pin on the chip. Depending on whether we have set the pin to be an input or output, the contents of the location will either go high or low. So we have 8 pins in the port A, 8 in port B, 8 in port C, 8 in port D, and 4 pin in the port E. And how it is there? There is one more thing. So ports registers. So these are the port registers called, through which the pins are connected. Now these ports are IO in a nature. They have the input and output both. But at a time, they can be either an input or an output. So like for an example, if you are designing some of a project, if you have connected a LED device with your pin, with one of the pin, the LED is an output device. Now it can't take input. So whenever, as per our hardware design, as per the devices, as per the peripherals we have connected with the microcontroller, we have to decide that whether the pin is input in a nature or an output in a nature. So that's how the pins has to be told the IO, the input or output. So that's how for each of the port register, there is a one more trace register called. So for port A, there is a trace A. For port B, trace B. Port C, trace C. O for port D, it is a trace D. And for port E, there is a trace E. So trace is tri-state actually. If you set it into an input mode, it will set the port as an input. If you set trace as an output mode, it will make the port as an output. If the port is an input, it means whatever the voltage present on the pin, that will be read by the port. If the port is set as an output, it means whatever the voltage, whatever the value is written on the port, that is either 0 or 1, it will be reflected in terms of the voltage on the pin. So for each of the port, there is a traces there. And if we write 0 in a trace, it means the port becomes output. If we write 1 in the trace, it means the port pin becomes input. So 0, it seems like a O, that is an output. 1, it seems like an I, and that's why it is an input. So always, whenever we will be writing the program, we have to first, in the very of the beginning of the program, we have to decide that whether the pin is an input or an output. And based on our configurations, we have to set the value of the trace and port in the very initialization, that whether it is a 0 or 1. If the pin, we want to set it in an output mode, the trace will become 0. If we want to set the pin in an input mode, the trace will become 1. So just keep remember this: trace 0, pin as output; trace 1, pin as input. Port 0, 0 volt on the pin; port 1, 5 volt on the pin. So like here we have a figure, and here from pin number 33 to 40, just here let's do. So on pin number 33 to pin number 40, here on these 4 pins, switches are connected, and all these 4 pins, the LEDs are connected. So switches are what? Input or output device?
Input.
Input.
Right.
And these are LEDs are output or input?
Output.
Output.
Output device. So we have 4 input devices connected on 4 pins, and we have 4 output devices connected on the 4 pins, and all of them are on the ports, port B. So if we have to draw a diagram, let me make it a little clear for you. So this is maybe a trace register. This is for port B, it is a trace B. And then we have a port B.
Where, sir? It's not visible.
I'm writing on the slide itself. Is it not visible?
No, sir.
Black pen. Now is it visible? My drawings on the slide itself.
No, sir.
No, sir.
But it is happening. Okay, let me do it. Paint is visible to everyone?
Yes, sir.
Yes.
Now drawing clear?
Yes, sir.
So it is a trace B. It is port B. And then we have the pins. Okay, my drawing is a little bad. Here we are having eight blocks. Same way for port also, we are having 8 blocks. Number starts from right side. Always remember, in this Harvard architecture, this is called little endian structure, and the counting always starts from right side. Whereas in Intel, the counting starts from left side. That is called the big endian structure. So 0, 1, 2, 3, 4, 5, 6, 7. Same way for the trace also, it is 0, 1, 2, 7. And here on RB0, it is pin number 33. This is 34, 35, and so on. It goes to 40. Now our switches were connected on pin number 40, 39, 38, and 37. Switches were connected. And from 36 to 33, the LEDs were connected. So it means these 4 pins should be set as an input, and these 4 pins needs to be set as an output. So for that, setting the pins as an input or output, we need to work with the trace register. So trace B, how do we write it? Trace B is equal to, it is 7, 6, 5, and 4. These all should be set as an input. So for input, we have to write 1. So 1, 1, 1, and 1. And for output, we have to set it as a 0. This should be set as a 0. And the 0 is set for output, we have to set it as a 0. So we will be writing here 0, 0, 0, and 0. So this is the setting of the trace, which will make pin number 40, 39, 38, and 37 to set as an output, and pin number 36 to 33 to, sorry, I'm wrong here, to set as an input, and pin number 36 to 33 will be set as an output. Here we are writing this in a form of a binary. So we will be writing 0 and B. That is the annotation that whatever we are writing is in form of the binary. And it is for 8-bit, it is easy to write in the form of a binary. If you prefer to write in the hexa, so for hexa it is 0x, and this is F0. So this is the value of the trace B if we have connected 4 switches and 4 LEDs on our pins. And then it is the port. So we need to initialize the port also. So now on port B will be, initially if you want to keep all of them as a off, all the LEDs as a off, so it will be 0, 0, 0, 0, so that 0 volt will be reflected on the pin. And here, once the switch will be pressed, that's what we have to read. But initialization of the switches always remain in a high stage. So that's why it will be 1, 1, 1, and 1. For port B, again, it is the same thing. 0B, 1, 1, 1, 1, 0, 0, 0, 0. And for trace, it is used for setting of the direction. It is 0B, 1, 1, 1, 1, 0, 0, 0, 0. If we want to keep the LEDs on initially, then in place of these 4 zeros, we will make them as a 1, so that 5 volt will get reflected on the pin and LEDs can turn on. So this setting of the trace and port is little clear now, because this is the first thing that we will have to do while doing the program.
Sir.
Is it clear to everyone? Or any, because this must be clear.
It's clear, sir.
Yes, sir. Yes, sir.
Okay. In Arduino, if you have done the programming, what you write there? Output and input you set, na? Pin numbers. You write the pin number and then comma output or comma input. You remember? Have you written any program for Arduino?
No,
Pin,
sir.
pin mode is the function, and in pin mode you write the pin number and then output or input. That's what you use to write. So it means you are doing the same thing, but actually that is in a high level language it is written. But actually at the end of the day, the pin number is connected with any of the register, and that register needs to be set. So actually whenever we are writing, the Arduino which we use is only for the purposes of the prototyping remains, because of the high level language in the nature. We don't have okay, Gafoor is not hearing me. Just ask him to connect on audio. He is not connected on audio. So just ask Gafoor to connect on audio. There is an icon of a mic on his Zoom, and there he has to connect. Furkan, if you can guide him. Okay, so in Arduino, it is a high level language. We have a less of a flexibility, but once we are doing the any kind of a industrial level of a program writing, there we have to deal with the SFRs, and that's where we need to set each and every bit of the registers so that we can get the direct control on the microcontroller. So that's how this direct control on the port pins are possible through writing through the SFRs. So this is a one example for writing on the SFRs. We will be using, once we will be writing the programs, we will be using the same concept to deal with any of the port pins of the microcontroller. So apart from this, the pro ports, there is the program memory is there, and this program memory writing requires a special circuitry. And for that purpose, there is a 5 volt of the voltage is required. And there is a programmer we will be using in the lab. So on that, there are the 3 pins. So in the microcontroller, there is the 3 pins. This ICSP DAT, ICSP clock, and PGM. These 3 pins are required to be connected with the computer through some means. And on your phone, there is a mic icon, and just near mic icon, you will have an option to connect on audio. So just connect. Okay, he's not hearing. Okay, so these 3 pins are required to connect with the computer, and only then whatever the program we are writing, they will get converted in the hex file and can be transferred, can be burnt into the memory of the microcontroller. And also for that, we require a special device that is called the programmer device, programmer and debugger device. And using that device, we will be feeding the program into the memory of the microcontroller, and it will happen. So when power is first applied to a computer, there is a lot of unknown stuff. The contents of the memory and registers are random, and the program memory remembers what we put into it. The program counter contains a 0 on the power up. The PIC has a clock whose frequency can be set with a crystal or resonator or RC circuit. the PIC even has a clock on board. So like internal clock, which we don't need to add any frequency controlling circuitry. So in many of our microcontrollers, there is an internal clock. In some of them, there we need to add the external clock. So the PIC 16F887, which we are using, is having the internal clock. We don't require any external clock circuitry to add it. Using the internal clock only, we can execute the instructions. Once the PIC gets powered up, the clock starts ticking, and on every tick of a clock, there is some instruction that will get executed. Every instruction here takes 4 cycles of the clock. So here instructions takes like fetch, decode, execute, and out. So every instruction has 4 steps. First, the instruction is fetched on the location, then it is get executed, then it is decoded, then it is executed, and then the output, it is put on the output lines. So every instruction takes 4 cycles of the clock. Here, instruction execution timing, if we are using 4 megahertz of a clock with the microcontroller, the instruction execution timing is 1 microsecond. If it is a 8 megahertz of a clock, what would be the instruction execution timing? One instruction takes how much time? If it is a 8
2
megahertz,
microseconds.
2 microseconds.
Zero 0.5.
Yeah. If frequency is increasing, the time will be the reverse of it, right? So half it will be 0.5. Same way, if it is a 20 megahertz, it means 5 times the frequency has increased. So 5 times the timing will be reduced. That's why it is the 0.2 microseconds, right? So whenever the question will come in front of you that if we are using this amount, this much of a megahertz of a clock, what would be the instruction execution timing? So you can take this reference and can calculate it, right? How many times your frequency has increased, the number of times the timing will be reduced. So we will be using 4 megahertz and 8 megahertz, which is available in the microcontroller itself. Up to 8 megahertz of a clock is available. We will be using that 8 megahertz clock for execution of the programs. So our instruction execution timing will be varying in the range of 1 microsecond or 0.5 microsecond. On our boards, once the boards which you will get in the lab, they will have the crystals also. So some of the times, if you require some high speed program to operate on, then you can use this 20 megahertz crystal also, and that time your instruction execution timing will be 0.2 microseconds. So you can think of that, how fast the program executes in the world of the microcontroller. At a speed of a 0.2 microsecond, the instruction gets executed and all our activity gets happened. That's what the beauty of the real-time systems design. So PIC basically work like any computer. It just relentlessly picks one instruction after another. Instruction may tell it to load the working register, do some math, store the result. And whenever we have to impact the outside world, these are the IO pins through which the outside world is impacted, or any of an input that you can read from the outside world. So your eyes, ear, nose, everything is through the IO pins. Through the IO pins, you can interact with the real world. And then there are the internal peripherals through which you can get the control on the real world peripherals. So that was the session today, giving you the introduction on the microcontrollers, embedded systems and all. Next part, it will be the giving you the knowledge on the MPLab XID and the C compiler, which we are going to use in the lab. And then we have 2 sessions on the C language. So giving you the complete knowledge on the embedded C. And then from next week onwards, we have the sessions in the lab directly, where we will be having the introduction on the peripherals first as a part of a lecture, and then you will be developing the applications in the lab using the hardwares. So this week, tomorrow also, our session will remain online. I will be letting you know about the MPLab XID, C compilers, and then C language will also be online. So this week sessions will be remaining online, and next week onwards, we will be coming in the lab and doing the things. Timing will remain the same. The links will be sent you separately for each day. Is this clear?
Thank you.
you.
Yes.
Any questions? If you have, you can ask me. Hope all of you have received the this LMS link now.
Yes, sir.
Some of them have joined also. So from Edredo, the LMS link has come to you. This is the, it is open. Okay. Okay, few of you have joined already, and I'm coming back to the classroom. So this is your LMS link. Yesterday's session is already uploaded. You can have a view of the session. Now, for every day, it is you have to go to the courses, and here it is the orientation session. Now it will be uploaded the first day, introduction to embedded systems. So after, by evening, this video will get uploaded, and the support materials will also get uploaded, and the notes are also, we will be providing you notes also. So every of our related materials will get uploaded over here, and you can go to view, and it will be uploaded in a form of a chapter, and you can go and review all of the things, right? So every of a session that gets completed, for which the materials will be get uploaded on your LMS, this will remain available to you. You can review and revise any of a time. Whenever I need to assess you, I will be giving you the quizzes and the assignments. Today I'm not giving, but from next day onwards, the assignments will be starting, and then you will have to follow those assignments also. Today it is the task that you have to review these things. You have to go through the data sheets and the notes which will be provided to you, have a understanding of the embedded systems, so that we have a strong foundation, and then we can do the programs in a very swift manner. Okay, so registers declared variable. So variables which you are declaring are stored in the RAM, whereas registers, the registers are two types. One is the general purpose registers. So general purpose registers are your RAM actually, which takes care of the variables. And special function registers have the separate locations. Those are the fixed locations, as I have shown you in the data sheet, that the special function registers have the particular locations, and whatever the value we declare for these special function registers, they are stored at their location only. It does not go into RAM. Okay. Any more questions? Later on, while revising, also if you face any time issue, so you can write your question over here. Either create post or ask under using the ask question. You can write a question over here, and I'll see it and answer over it. The timing will remain same, 9:30 to 1:30. Online, we are starting at 9:30. Once we will be coming in the offline, again, the same timing will be there from 9:30 to 1:30. Okay, so you can ask the questions also over here using the LMS. Also, one more thing, if you want to access this on your mobile phone, so app is also available in the same name. The Android app is available in name of Edredo. You can go to your Play Store, you can download the Edredo app and use the same login which through which you have logged in here. So you can access the same materials on your app also. So that was it. Tomorrow we are meeting again for the MPLabX ID, C language and all. Right now, if you don't have any question to anyone, I can end the session.
Sir, 1 minute. Where can we find the link, sir? The same link will be directed to the app, sir, or
App for app, you have to go to Play Store and
Yes,
type
sir.
Edredo over there.
Okay, sir. But after downloading or
Yes.
installing,
Yes.
when we can, how can we direct us to that the perfect link?
First on the browser, here you have right. Here you have
Yes.
created your account.
No, sir.
Yes. Okay. So you have a link. You have received an email. On your email, the
Okay,
link
sir.
has the link to join this LMS has been given. You have to first join the LMS, create your account as a student, and then once you have joined over here, then you can download the app and use the same login ID and password to log on the app also. You will be on both of the platform.
Okay, sir. Thank you, sir.
Okay, so I'm ending the session now. It was a pleasure interacting with you all, and thank you for being a patient listener. Have a wonderful day ahead. Just keep a revision of all the things and be a serious learner throughout this month so that we can do something better out once we are in the project and in the internship.
Okay, sir. Thank you, sir.
Thank you. Have a wonderful day. Okay, there is one more question. Int size on PIC. No, the embedded C, the int size here in the cross compiler, it is 2 bytes. Okay, thank you. I'm ending it. Bye.